There is a sound in your home or in your memory that vibrates at roughly 25 to 50 cycles per second, a frequency range that researchers have associated with reduced stress responses, improved tissue repair, and measurable changes in the nervous system. It is not engineered. It is not synthetic. It does not come from a machine. It comes from a cat. Before we move slowly into the quiet of tonight, before the room softens and the light turns warm, it is worth knowing this. The sound we are about to follow has been studied in laboratories, recorded in clinical environments, and analyzed by neuroscientists who were trying to understand why something so gentle could have such measurable effects. Now the room can settle. There is a specific kind of quiet that arrives at night, the kind where the day loosens its grip, where the air feels softer, and where your breath begins to lengthen without you asking it to. Maybe you are already lying down. Maybe the pillow has finally found its exact place beneath your head. Maybe there is weight on the blanket, the reassuring kind, the kind that tells your nervous system that, for now, nothing urgent is coming. Welcome to Deep Science Sleep. I am so glad you are here. Tonight, we are going to follow one of the most quietly extraordinary sounds in the natural world. Not as metaphor, not as poetry, but as biology, as physics, as vibration moving through muscle and bone. The neurologically generated purr of a domestic cat, one of the most studied vocalizations in animal science, and still one of the most mysterious. Over the next few hours, we will move through it together. How the purr is produced inside the larynx, why its frequency range is so unusual, what evolutionary advantage it may provide, and what current human research suggests about its calming and restorative effects. Slowly, gently, at the pace of something that does not need to rush to be understood. So let your eyes grow heavy, let the edges of the room blur, and let us begin. The sound that stops time. Imagine for a moment that you are sitting in a chair, an ordinary chair in an ordinary room. The hour is somewhere in that soft territory between late evening and true night. A cat has settled itself onto your lap, not dramatically, not with announcement, but in the way cats always arrive at their chosen resting spots, which is to say, as though gravity simply made the decision and they had nothing to do with it. The cat turns in a small circle, presses its forehead against the heel of your hand once, and then collapses into a warm, breathing oval of fur. And then, somewhere inside that small animal, something begins. It is barely a sound at first, more like a feeling, a vibration that travels up through your thighs and into your chest before you have even consciously identified it as a noise. It is rhythmic and low and curiously even. The same on the breath in as on the breath out, a steady mechanical hum that your body registers before your mind does. By the time you become aware that you have been listening to it, you have already been listening to it for a while. This is the purr. And the first thing science wants you to know about it is that it is not what you think it is. Most of us, from the time we were small children, learned that a purring cat is a happy cat. We learned it the same way we learned so many things about the world, through observation and imitation and the accumulated wisdom of people who had lived with cats before us. And there is truth in that learning. Cats do often purr when they are content, when they are warm, when they are being touched by a person they trust, when the food bowl has just been refilled and the world is in order. But the purr is far stranger and far older and far more layered than simple contentment. Cats purr when they are in pain. They purr when they are afraid. They purr during the long, difficult work of giving birth. They purr when they are recovering from surgery, lying still in their carriers with their eyes half open and the world tilted sideways. They purr in the veterinarian's office, pressed flat against the examination table with their pupils wide and their heartbeats quick. They purr, according to researchers who have spent time with them in shelters. Even in the most stressful environments any cat can find itself in. This tells us something important. The purr is not simply a signal that everything is fine. The purr is something the cat does for itself, to itself, with itself. Something it generates from within when the world has become large or painful or uncertain, as though the body already knows the medicine and has simply learned, over millions of years of evolution, to manufacture it. We will come back to this. We will spend a great deal of time with this idea, because it is the heart of what makes the purr so scientifically fascinating. But first, let us slow down even further and spend some time just sitting with the sound itself. With the quality of it, the texture of it, the way it moves through space. Sound, as you may know, is not really a sound at all in the way we tend to imagine it. Sound is vibration. It is the mechanical movement of air molecules, pressed and stretched in rhythmic waves that travel outward from a source and are eventually received by the specialized cells lining the inside of our ears, which then translate those waves into electrical signals that our brains interpret as a particular experience. The sound of a cat purring, at its lowest frequency, travels at approximately 25 cycles per second. 25 times every single second, the air pressure rises and falls in that steady, regular pattern. To put that in perspective, the lowest note most humans can sing is somewhere around 80 to 85 hertz. A bass guitar, when playing its deepest open string, produces a note at around 41 hertz. The rumble of a large truck engine sits somewhere around 60 to 70 hertz at idle. The purr, at its lowest, sits below all of these. It is one of the deepest sounds you will commonly encounter in domestic life, and it carries with it, as we will explore in great depth, properties that make it unlike almost any other everyday sound. There is also something about the purr that is unique among all the sounds that cats make, and unique among almost all the sounds that any mammal makes. The purr happens on both sides of the breath. When a cat inhales, the purr continues. When it exhales, the purr continues. There is no gap, no silence, no pause for the mechanism to reset. It is a continuous sound, a loop, an unending circuit of vibration that runs through the entire respiratory cycle without interruption. Other vocalizations, meows, chirps, yowls, growls, happen only on the exhale the way human speech does. The purr is singular in its persistence. This persistence, as it turns out, is one of the keys to its mystery. And to understand why it works the way it does, we need to travel somewhere a little unusual. Deep into the cat's throat, past the soft fur and the warm skin, down into the architecture of the voice box itself, because that is where this story truly begins. There is also a reason that the purr affects you the way it does when you hear it, a reason that goes beyond simple familiarity or positive association. The human auditory system has what researchers sometimes describe as a bias toward rhythmic, low-frequency, repeated sounds in the lower registers of hearing. These sounds, the heartbeat, the breath, the low hum of wind through grass, are sounds that our nervous systems have been calibrated to respond to with something close to ease. They are sounds associated with safety, with the interior of warm spaces, with the feeling of not being alone. The purr, sitting at 25 to 150 hertz and maintaining that steady, unwavering rhythm through every cycle of breath, lands directly within this range of instinctive comfort. It is not a coincidence that people who listen to recorded cat purrs while trying to fall asleep often report that the effect feels immediate and almost physical. A dropping of tension in the chest, a softening of the jaw, a slowing of thought. The nervous system is not being tricked. It is responding precisely as it was designed to respond. Before we move deeper into the biology, let us pause for just a moment and let this settle. You are listening tonight to a sound that has existed in some form for tens of millions of years. A sound that was being made in some version of itself long before the first humans walked the earth. A sound that carries, embedded within its simple rhythm, an extraordinary weight of evolutionary history, biological function, and quiet therapeutic power. The cat on your imaginary lap does not know any of this, of course. It is simply warm. It is simply there. And it is purring the way it always has, the way all cats have, because that is what bodies like its know how to do. Close your eyes a little. Let the image settle. We are just getting started. The architecture of a purr. How it's made. For a very long time, the mechanism behind the purr was genuinely mysterious. Scientists who studied animal vocalizations in the mid-20th century puzzled over it in ways that might seem strange to us now. The cat was right there, plainly making the sound, and yet the question of exactly how it was making the sound, through what physical process, driven by what biological machinery, turned out to be far harder to answer than expected. Part of the difficulty was the sound itself. Most vocalizations in mammals, including every sound a human makes, work on a fairly straightforward principle. Air from the lungs passes through the larynx, which is the voice box, and sets the vocal folds, sometimes called the vocal cords, into vibration. The vibrating folds produce sound waves, and those waves are then shaped by the mouth, the lips, the tongue, and the throat into the specific pitches and timbres we recognize as particular sounds. This is called the myoelastic aerodynamic theory, and it is the scientific explanation for essentially every sound a human being has ever made. But the purr does not follow these rules cleanly. The purr happens on both the inhale and the exhale, which means the airflow driving it reverses direction every breath cycle, and yet the sound does not change or stop. Typical vocal fold vibration does not work like this. When air flows inward rather than outward, standard vocal fold mechanics break down entirely. The folds simply do not vibrate in a way that produces a coherent sound. And yet the cat goes on purring, in and out, without a hiccup. For decades, the dominant explanation was something called the active muscle contraction hypothesis, sometimes abbreviated as AMC. According to this theory, the purr was produced not by passive vibration of the vocal folds driven by airflow, but by rapid, rhythmic, voluntary muscle contractions in the larynx. The cat was, in essence, actively squeezing and releasing the muscles in its voice box in a precise, repetitive pattern timed exactly to match the purring frequency. A neural oscillator somewhere in the brain, a cluster of neurons firing in a set rhythm, was thought to be sending repeating electrical signals down to the laryngeal muscles, causing them to contract and relax somewhere between 25 and 150 times per second, which then produced the sound. The neural oscillator part of this theory has substantial support. Researchers who have studied cats in laboratory settings found evidence that interrupting the nerve pathways to the larynx could eliminate purring, which strongly suggested a brain-driven, actively controlled mechanism. And the idea of a central pattern generator, a set of neurons in the brainstem that produces rhythmic output without needing continuous sensory input, is well established in biology. These kinds of oscillators drive breathing, walking, swallowing, and many other rhythmic behaviors, and it was perfectly plausible that one of them drove purring. But then, in 2023, a team of researchers at the University of Vienna did something that changed the picture considerably. They took the larynges, the voice boxes of 8 domestic cats. These were larynges that had been carefully preserved from cats that had died of unrelated causes, so they were complete and intact anatomically, but they contained no living neural tissue. They were, in short, disconnected from the brain entirely. No nerve signals coming in. No active muscle contractions possible. Just the raw mechanical structure of the cat's voice box, kept moist and warm and supplied with airflow from external sources. And when the researchers blew air through these isolated larynges at pressures similar to normal cat breathing, something unexpected happened. They purred. All 8 of them. Every single excised larynx, with no neural input, no muscular control, no brain involved in any way, produced self-sustained oscillations at frequencies between 25 and 30 Hz, the exact range of the lower end of a normal cat purr. The sound was not identical to a living purr in every detail, but the fundamental frequency was there, consistent and repeatable. This finding, published in the journal Current Biology, does not, as the researchers themselves were careful to note, completely disprove the neural oscillator theory. What it does is establish that the cat's larynx has physical properties that allow it to produce purring frequency vibrations passively, without any active muscle involvement at all. The structure itself, when airflow passes through it, will spontaneously oscillate at this frequency. When the researchers looked more closely at the anatomy, they found the reason. Embedded within the vocal folds of the cat larynx were small masses of connective tissue, up to about 4 millimeters in diameter, that significantly increased the density and mass of the vocal folds. This extra mass is precisely what allows the folds to vibrate at such unusually low frequencies. Normal vocal folds, lighter and thinner, vibrate much faster. That is why the human voice sits in the hundreds of hertz rather than the tens. The cat's vocal fold pads act like weights, slowing the vibration down, pulling the natural oscillating frequency of the tissue into that deep, low register that we recognize as the purr. The researchers proposed a synthesis. What probably happens in a living, purring cat is that both mechanisms are at work simultaneously. The passive mechanical resonance of the weighted vocal folds, driven by the normal aerodynamics of breathing, produces a natural oscillation at or near purring frequency. And the neural oscillator in the brain sends rhythmic signals to the laryngeal muscles that are frequency entrained to this passive resonance, not creating the vibration from scratch, but amplifying and stabilizing it, keeping it consistent, perhaps modulating it in response to the cat's emotional state. This is an elegant biological solution. Instead of burning energy on active muscle contractions 125 times per second, the cat's body has evolved a passive mechanical system that produces the purr almost for free, powered only by the ordinary airflow of breathing, with neural input providing fine-tuning rather than primary generation. This is significant, as we will see later, because it means purring costs the cat very little in metabolic terms. It is available essentially any time, at almost no physiological expense. Now let us add one more layer to this picture, because there is another structure involved in purring that we have not yet discussed, and it is a structure with an interesting story of its own. In the throat of every cat, and in the throats of all mammals, including humans, there is a small, U-shaped bone called the hyoid. The hyoid is unusual because it is the only bone in the human or cat body that does not articulate directly with any other bone. It floats, suspended by muscles and ligaments, in the middle of the throat, acting as an anchor point for the tongue and for the muscles that move the larynx. In humans, the hyoid is fully ossified. It is a complete solid bone. In most other mammals, it is similarly complete. In cats that can purr, which includes domestic cats, cheetahs, cougars, bobcats, lynxes, ocelots, and most of the smaller wild feline species, the hyoid bone is also fully ossified and rigid. When the larynx vibrates at purring frequencies, this rigid hyoid bone resonates sympathetically, like a tuning fork struck by another tuning fork nearby. The vibration of the vocal folds sets the hyoid vibrating, and the vibrating hyoid amplifies and transmits the purring vibration through the bones of the skull and down through the body. This is why you feel a cat's purr as much as you hear it. When a cat is resting on your chest, you are receiving those 25 to 150 Hz vibrations not only through the air and into your ears, but also through direct mechanical contact. Through your skin and muscle and bone, where they travel in the same way that sound travels through the earth in a low-frequency earthquake, felt in the body before it is heard with the ears. The vibration is inside you. And as we are about to discover, that matters enormously. The frequency secret, 25 to 150 Hz, and why it matters. Let us talk about numbers for a moment. Specifically, let us talk about the number 25, the number 50, and the number 150, because these three numbers sit at the heart of one of the most intriguing and most discussed aspects of the cat's purr. A cat's purr, as we have established, operates within a frequency range of approximately 25 to 150 Hz. But within that range, the sound is not uniformly distributed. Acoustic measurements of cat purring consistently reveal two prominent peaks. Two frequencies at which the energy of the purr is particularly concentrated, like the ridges of a mountain range rather than a single flat plateau. The first peak sits in the range of approximately 25 to 50 Hz. This is the low range, the deep range, the range where you feel the purr in your bones before your ears have fully registered it. The second peak sits in the range of approximately 100 to 150 Hz, which is higher, still well below anything that would be called treble, but noticeably warmer and brighter in texture than the lowest vibrations. These two peaks would be interesting enough simply as a description of the acoustic properties of cat vocalizations. But what makes them genuinely remarkable is where else these frequencies appear. Researchers studying vibration therapy, the medical application of low-frequency mechanical vibrations to tissue, have known for decades that specific frequency ranges have specific effects on biological tissue. The field is sometimes called vibroacoustic therapy or mechanotherapy, and it has produced a substantial body of peer-reviewed research on the physiological effects of delivering controlled vibrations to the human body at precise frequencies. And what those researchers have found is this. Vibrations in the range of 25 Hz are particularly effective at stimulating bone growth and strengthening bone tissue. Vibrations at approximately 50 Hz are among the most effective frequencies for promoting bone repair and fracture healing, specifically through the activation of osteoblasts, which are the cells responsible for building new bone. A 2017 study published in the Iranian Journal of Basic Medical Science, for example, exposed laboratory rabbits with bone defects to vibrations at 5 different frequencies: 12.5 Hz, 25 Hz, 50 Hz, 100 Hz, and 200 Hz, and found that the 25 and 50 Hz groups showed dramatically superior healing with denser new bone formation, greater osteoblast activity, and faster reconnection of the damaged tissue than all other groups. The frequency of 50 Hz, in particular, has emerged across multiple independent research lines as something close to optimal for stimulating bone marrow stromal cells to differentiate into osteoblasts and generate new bone. Studies at the Dalian Medical University in China found that exposure to 50 Hz vibration for 30 minutes per day significantly upregulated the genes associated with osteogenesis, including the key bone-forming transcription factor called RUNX2, as well as collagen type 1 and osteoprotegerin. These are not marginal effects. These are measurable, reproducible, histologically verified changes in how bone tissue behaves. And the cat's purr sits squarely within this range. Not approximately, not roughly. The dominant lower frequency peak of a cat's purr corresponds to the exact frequencies that researchers have repeatedly identified as most effective for bone healing and bone strengthening in laboratory and clinical studies. This is what Elizabeth von Muggenthaler, a researcher at the Fauna Communications Research Institute, found when she systematically recorded and analyzed the purrs of 44 felids, 44 individual cats from several different species, including cheetahs, ocelots, pumas, servals, and domestic cats. Every single one of them produced strong fundamental frequencies between 25 and 150 Hz. And domestic cats, servals, ocelots, and pumas specifically produced dominant frequencies at exactly 25 Hz and 50 Hz, the two frequencies most associated with bone growth and fracture healing in the medical literature. This overlap is so precise and so consistent across so many species that researchers have begun to describe it as the basis for a hypothesis that the purr, at least in part, evolved or was maintained by natural selection specifically because its frequencies promote healing in the cat's own body. Consider the cat's lifestyle. A healthy domestic cat sleeps somewhere between 12 and 16 hours per day. Wild felids rest even longer when not actively hunting. Extended periods of inactivity, as any physiologist will tell you, are not benign for the musculoskeletal system. Prolonged rest leads to bone density loss, muscle atrophy, and connective tissue weakening. Astronauts in zero gravity who cannot engage in normal weight-bearing activity face accelerated bone loss that is one of the serious challenges of long-duration spaceflight. And the solution that NASA and space medicine researchers have investigated? Low-frequency vibration therapy at exactly the kind of frequencies a cat's purr produces. Scientists at the University of California's School of Veterinary Medicine, including researcher Leslie Lyons, have pointed out that cats show remarkably low rates of bone disease and musculoskeletal problems compared to dogs of similar size and activity level. They do not develop the degenerative bone conditions that comparable mammals frequently develop. They heal from fractures with exceptional speed. They land from extraordinary heights with survivable injuries at rates that continue to surprise veterinarians. And the hypothesis that vibrating their own bones for 12 to 16 hours a day, at frequencies that laboratory research identifies as optimal for bone maintenance and repair, might have something to do with this is not a fringe idea. It is taken seriously by researchers in the field. The second frequency peak, the one in the range of 100 to 150 Hz, is associated in the vibration therapy literature with different effects. Research suggests that frequencies in this range are particularly useful for pain relief, for reducing swelling and edema, for promoting wound healing, and for stimulating muscle growth and repair. When cats purr in situations of pain or distress, which, as we noted at the beginning, they demonstrably do, the self-generation of vibrations in this frequency range may be functioning as an endogenous analgesic mechanism. the body creating its own pain relief through the mechanical properties of its own voice box. It is important to say clearly that this remains a hypothesis, not a confirmed fact. Direct experimental proof that a cat's own purring causes measurable improvements in its bone density or wound healing speed has not yet been established to the standard of clinical certainty. The evidence is correlational and comparative. The frequencies match, the biological effects of those frequencies are documented elsewhere, and cats show the outcomes we would expect if the hypothesis were true. But the specific causal mechanism has not been isolated and proven in a controlled experimental setting in the way that rigorous science requires before a hypothesis becomes a confirmed fact. What we can say, and say with confidence, is that the match is remarkable, that it is unlikely to be purely coincidental, and that the same frequencies that a cat produces continuously for most of its waking and resting hours are the same frequencies that medical researchers have independently identified through completely separate lines of investigation as effective tools for stimulating bone formation, reducing inflammation, and promoting tissue repair. The cat arrived at this solution without a laboratory, without a researcher, without any explicit knowledge of any of this. It arrived through 400 million years of vertebrate evolution and something like 10 to 12 million years of feline evolution, selecting for a behavior that appears to maintain the health of an animal designed to spend an enormous portion of its life lying very still. That is not magic. That is biology doing what biology does, finding elegant solutions to hard problems, then running them for long enough that they become invisible. Now breathe with me for a moment. Let the numbers settle. Let the picture become whole. A small animal is lying very still, somewhere warm, and the inside of its throat is generating a sound at a frequency that laboratory researchers measure in controlled experiments and publish in academic journals. The sound passes through its own body, and through yours if you happen to be nearby. And it may be gently, measurably, over time, doing something useful in both of you. The ancient reason, the evolution of the purr. Before there were domestic cats, before there were houses or laps or ceramic food bowls, before any version of this quiet compact between humans and cats had been arranged, there was a small feline moving through grassland or forest, and it was purring. We do not know exactly when purring evolved in the cat lineage. The fossil record does not preserve soft tissue with enough detail to tell us when the vocal fold pads that enable feline purring first appeared. What we do know is that the capacity to purr is found across a very wide range of feline species, across animals separated by millions of years of divergent evolution, which suggests that the trait appeared early in the history of the family and was retained because it was useful. The earliest context in which purring is almost certainly significant is the relationship between a mother cat and her newborn kittens. Kittens are born in a state of extraordinary vulnerability. They arrive into the world blind and deaf, their eyes and ear canals sealed shut, their nervous systems immature, their thermoregulatory systems not yet capable of maintaining their own body temperature. For the first week or two of life, they exist in a world defined almost entirely by touch, smell, warmth, and vibration. They cannot hear sounds in the conventional sense, but they can feel vibration. The mechanoreceptors, the pressure-sensitive cells in the skin and deeper tissues, are among the earliest sensory systems to become functional in mammalian neonates. And the first thing they feel, in that first world of warmth and darkness, is their mother purring. A mother cat purrs almost continuously during nursing, during the long, still hours when the kittens are feeding and the family is at rest. The kittens, pressed against her body from all sides, are bathed in those vibrations. Researchers believe this serves at least two distinct functions. First, it guides the kittens toward their mother and toward the nursing position. The vibration acts as a tactile beacon, a way of saying, "Here I am, here is warmth, here is nourishment, come here, you are safe." In an environment where they cannot see or hear in the ordinary sense, this is not a trivial service. The second function is more subtle and more profound. When the kittens themselves begin to purr, which they can do within the first few days of life, at some of the earliest points of observable behavior, they are feeding back into the system. A nursing kitten that is purring is communicating something to its mother. "I am feeding, I am content, I am well, do not move, do not stop." The purr becomes a dialogue, a mutual signal passed back and forth between the small and the large, between the one who provides and the one who receives. The mother purrs, and the kittens purr back, and the shared vibration becomes a kind of language spoken in the register that neither of them yet has words for. This is why kittens can purr before they can do almost anything else. The mechanism is functional from the first days of life because it needs to be. The survival advantage is immediate and direct. Kittens that could effectively signal their feeding status to their mothers were kittens that survived. And so the neural and anatomical machinery that generates purring was shaped by selection at the very earliest point of a cat's life. As the kitten grows, the purr does not disappear, it expands in function. Adolescent cats purr during play, during social grooming, during times of uncertainty and stress. The self-soothing function that we described at the beginning of this journey, the way the cat turns its purr inward when the world becomes difficult, appears to be an extension of this early comfort system, a way of recreating internally the sensation of safety that was associated, in those first weeks of life, with warmth and closeness and the mother's vibration. Adult cats continue to use the purr in social contexts, though with notable changes. The purr of an adult cat directed at a human, researchers have noticed, is structurally similar in some ways to the purr of a kitten directed at a mother, which may not be accidental. The domestication of cats over the past approximately 9,500 years has produced a creature that, in many respects, maintains behaviors that in wild cats are associated only with kittenhood. This is a pattern found across many domesticated animals. Selective pressure for traits associated with juvenile, non-threatening behavior. And in cats it expresses itself in, among other things, continued meowing and purring toward adult humans in ways that wild cats do not direct toward other adults. The cat, in other words, has learned, over thousands of years of shared life with humans, that purring works on us. Not cynically, not deliberately in any conscious sense, but through the ancient algorithm of natural selection. Cats that purred in human company were cats that received more food, more warmth, more protection, and more resources. And so the behavior persisted, was reinforced, became more elaborate and context-specific. Researchers at the Museum für Naturkunde Berlin and the University of Naples Federico II published a study, released in early February 2026, that found something remarkable about the cat's purr in the context of communication. While a cat's meow varies enormously depending on context, emotional state, and the individual cat's relationship with a particular human, becoming in some ways a learned and flexible language, the purr remains essentially constant, stable, individual, Researchers who applied acoustic analysis tools originally designed for human speech recognition found that they could identify individual cats reliably from their purrs but not from their meows. The purr is what the researchers called a vocal fingerprint, a stable acoustic signature that persists regardless of context or emotional state. This consistency makes the purr fundamentally different from the meow in its communicative function. The meow is flexible and context-driven, shaped by each cat's particular history with its particular human, variable enough to express an enormous range of needs and emotions. The purr is stable and identity encoding, a consistent signal that says not what I want but who I am, and more to the point that I am here with you, that this is a moment of closeness, that something between us is functioning as it should. There is also increasingly a genetic dimension to all of this. Research on the domestication of cats at the genetic level has begun to identify specific variations in genes associated with social behavior and vocalization that appear to have been selected for during the period of human contact. One study by researchers in Kyoto examined a gene called the androgen receptor, which shows a variable number of repeated sequences in different cats. Cats with fewer repeats in this gene appear to vocalize more, to purr more frequently, and to communicate more richly with humans than cats with more repeats, and this shorter repeat version was not found in the wild relatives of the domestic cat. It appears to have emerged and been selected for specifically during and after domestication. The purr, in other words, is not simply an ancient behavior that cats happen to still perform. It is, in part, something that has been shaped and refined by 10,000 years of living alongside human beings, something that has co-evolved with us, tuned to our nervous systems in ways neither party ever consciously negotiated. We domesticated the cat, at least partly, but the cat, in its quiet way, domesticated something in us as well. And the purr is the most beautiful evidence of that negotiation. Purr versus roar, the great feline divide. Not all cats purr. This is a fact worth dwelling on for a moment because it tells us something important about what purring actually costs, anatomically speaking, and what it buys. Among the approximately 36 to 40 species of wild cat that exist today, roughly 20 can produce some version of a purr. The others, specifically the 4 true big cats of the genus Panthera, which are the lion, the tiger, the leopard, and the jaguar, cannot. What they can do instead is something that a domestic cat would find entirely unimaginable. They can roar. The distinction between the purring cats and the roaring cats comes down to anatomy, specifically to the structure of the hyoid bone and, more precisely, to the vocal folds. We have already discussed the hyoid in the context of the domestic cat's purring mechanism. In the roaring cats, the arrangement is fundamentally different. In lions, tigers, leopards, and jaguars, the connection between the hyoid bones and the skull is not a rigid bony linkage but an elastic cartilaginous ligament. This ligament allows the larynx to stretch, creating a significantly larger resonating chamber than a rigid connection would permit. The vocal folds themselves in roaring cats are larger, longer, heavier, and more elastic than in purring cats, with a specialized layer of fatty elastic tissue that allows them to be pushed far apart and snapped back together with enormous force. The result is a sound of extraordinary power. The roar of a lion can reach approximately 114 decibels at close range and can be heard up to 5 miles away in open terrain. It is loud enough at close quarters to approach the threshold of pain for human hearing. But this anatomy that enables roaring precludes purring. The heavy, elastic vocal folds that can generate such enormous sound pressure at low frequency cannot perform the rapid, steady, low-effort oscillations required for a purr, and the elastic ligament connection of the hyoid, which gives the larynx the flexibility to roar, prevents the rigid resonance that the fixed hyoid provides in purring cats. The evolutionary trade-off is complete and apparently irreversible. You can have roaring or you can have purring, but the anatomy that produces one prevents the other. This tells us something useful. Both abilities were worth having for the animals that evolved them. The roar serves a profoundly different set of functions than the purr. It is a territorial claim broadcast across enormous distances. It is a social signal exchanged between members of a pride or a pair. It is an advertisement of size and health, a deterrent to rivals, an attraction to potential mates. It is the sound of an animal that does not need to be quiet. The purr serves a more intimate set of needs. It is close range. It is relational. It travels through bodies more than through air. It functions best when the cat is physically near another being, another cat, or over the past 10,000 years, a human. It is the sound of an animal that has found safety in proximity. Cheetahs occupy a fascinating middle position in this picture. They are, by any casual measure, large cats. An adult cheetah can weigh up to 72 kilograms and reach speeds of over 100 kilometers per hour. But anatomically, in the relevant respects, they are small cats. Their hyoid bone is fully ossified. Their vocal folds have the structure of a purring cat, and they can produce a continuous purr just as a domestic cat does. They cannot roar. Their unique vocalizations include a high-pitched chirping sound, almost bird-like in character, as well as purring and various other calls. A vocal repertoire that reflects their unusual ecological position as the fastest land animal, but not an apex predator in the traditional sense. Pumas, also called mountain lions or cougars, are similarly large in body but small in vocal anatomy. They purr. They also make a range of other sounds, including a haunting, eerie scream that has startled human hikers across the Americas for centuries. But they cannot produce the deep, rolling roar of a lion or tiger. Ocelots, bobcats, lynxes, and servals can all purr. Snow leopards present one of the most interesting edge cases. They are classified within the genus Panthera alongside lions and tigers, but they cannot roar in the traditional sense, lacking the fatty elastic layer in their vocal folds that enables true roaring. Snow leopards chuff, a breathy non-aggressive sound used for social bonding, and they make various other calls. But the snow leopard sits in an interesting gray area between the two great feline vocal traditions. The serval, which we mentioned in the context of Elizabeth von Muggenthaler's frequency research, is a medium-sized African wild cat famous for its extraordinarily long legs and large ears. It can purr, and its purring frequencies match those of domestic cats closely enough that the same therapeutic frequency arguments apply equally to the serval's own body. Wild cats in general, when they purr, appear to be doing so for the same broad suite of reasons as domestic cats: communication, self-soothing, and potentially self-maintenance, though the specific social contexts differ considerably from species to species. What is particularly striking about the evolutionary history of purring is its apparent antiquity. The feline family, Felidae, first appears in the fossil record approximately 25 million years ago. The divergence between the purring lineage and the roaring lineage is estimated to have occurred somewhere between 6 and 9 million years ago. This means that cats have been purring in some form with some version of this mechanism for an extraordinary length of time. The behavior predates the first hominids. It predates the evolution of the genus Homo by millions of years. It predates almost everything we tend to think of as defining the world we live in. The purr is old in a way that very few things we encounter in daily life are old. The specific neural patterns, the specific anatomy, the specific frequency range. These have been refined and preserved across millions of years of evolution, which is biology's way of saying, this works. Whatever this is doing, it works well enough to keep. And now you are here in the warmth of this night, and you are receiving the benefit of that 10 million year experiment directly. Through your ears, through your nervous system, through every cell that is still and quiet and listening. Living medicine, the purr as healing tool. We have talked about the frequencies. We have talked about the bone research. Let us now go deeper into the evidence, into the laboratories and veterinary clinics and physics departments where researchers have been trying carefully and rigorously to understand whether the purr does what it appears to do. The core claim, stated plainly, is this: the vibrations produced by a cat's purr fall within frequency ranges that laboratory research has demonstrated are effective for stimulating bone formation, promoting wound healing, reducing inflammation, relieving pain, and improving joint mobility. The further hypothesis, not yet definitively proven, but well supported, is that cats purr, at least in part, because the self-generated vibrations of purring help maintain their own musculoskeletal health during long periods of inactivity. Let us look at the evidence on the bone side first, because it is the most extensively researched. Research published in the Iranian Journal of Basic Medical Science in 2017 exposed 40 laboratory rabbits with surgically created bone defects to low-frequency vibrations at 5 different frequencies: 0 Hz as a control, 12.5 Hz, 25 Hz, 50 Hz, and 100 Hz for 30 minutes per day, 5 days per week, for 4 weeks. The results were striking. The animals in the 25 and 50 Hz groups showed dramatically superior bone healing compared to all other groups. Tighter integration of implanted tissue with the surrounding bone, higher density of new trabecular bone formation, stronger osteoblast activity, and elevated expression of the key osteogenic genes RUNX2, osteoprotegerin, precollagen type 1, and RANKL. The 50 Hz group showed the strongest effects overall. This study is one among many in a field that has been growing steadily for decades. Whole-body vibration therapy has been studied in postmenopausal women with osteoporosis, in children with conditions affecting bone density, in bedridden patients at risk for fracture, and in athletes recovering from musculoskeletal injuries. The consistent finding across a very large body of research is that low-magnitude vibration at frequencies in the range of approximately 20 to 90 Hz can stimulate osteoblast differentiation, increase bone mineral density, improve trabecular bone architecture, and accelerate fracture healing. One randomized double-blind trial published in the Journal of Bone and Mineral Research found that postmenopausal women who received 10 minutes of 30 Hz vibration daily for 1 year maintained bone stiffness at the distal tibia, while the control group showed decline. The cat purrs continuously for hours at a time at these exact frequencies. Not for 10 minutes, for hours. And it does this every day for its entire life. The comparison that researchers sometimes draw to make this vivid is to astronauts. One of the most serious physiological challenges of extended spaceflight is bone and muscle loss caused by the absence of gravitational loading. In zero gravity, the normal mechanical stresses that maintain bone density in a terrestrial environment are absent, and bone begins to demineralize at a rate that would be catastrophic over the timescales of interplanetary travel. NASA and space medicine researchers have therefore investigated low-frequency vibration therapy as a potential countermeasure, a way to provide the musculoskeletal system with the mechanical stimulation it needs to maintain itself even in the absence of gravity. The frequencies they find most promising are in the range of 30 to 60 Hz. Cats face an analogous problem. They are, by evolutionary design, animals that spend enormous amounts of time completely still, not hunting, not climbing, not doing any of the mechanical work that normally maintains musculoskeletal health. A cat that rests 16 hours a day without some compensatory mechanism would be expected to suffer progressive bone density loss. The purr, generating exactly the frequencies that bone maintenance requires, may be that compensatory mechanism, built-in, always available, requiring only that the cat breathe. It is worth noting, in the spirit of scientific accuracy, that evidence also exists for cats being less susceptible to bone cancer and degenerative joint disease than dogs, and that they show a well-documented ability to survive falls from extraordinary heights, the so-called high-rise syndrome in veterinary medicine, in which cats falling from great heights often survive with injuries that would be fatal in other animals, with fracture patterns that heal faster than comparable injuries in other species. Whether any of this is directly attributable to purring is not yet proven, but the correlation is real and it is consistent with the hypothesis. On the healing side, the evidence extends beyond bone. Vibrations in the 100 to 150 Hz range, the upper peak of the cat's purring frequency range, have been associated in research with reduced inflammation, accelerated wound healing, pain relief, and decreased swelling. One particularly interesting line of evidence comes from clinical applications of low-intensity pulsed ultrasound, or LIPUS, which operates in a frequency and intensity range that researchers have described as comparable to a cat's purr. LIPUS has been used clinically for decades to accelerate bone fracture healing and has also shown effects on soft tissue healing, reducing healing time for tendon and muscle injuries. Researchers have noted that the mechanism of LIPUS, mechanical stimulation of tissue at low frequency, causing cellular responses that accelerate repair, is conceptually similar to what the cat's purr delivers through direct vibration. There is even, in the realm of applied medical technology, an effort to use this insight directly. Researchers have experimented with medical casts equipped with audio transducers that deliver low-intensity vibrational stimulation at frequencies in the 25 to 150 Hz range, essentially embedding a cat purr frequency generator into the cast of a broken limb. The preliminary results suggest that this approach can accelerate fracture healing in ways consistent with what the frequency research would predict. For the cat itself, all of this machinery is invisible. The cat does not know about osteoblasts. It does not know about trabecular bone density or vibroacoustic therapy or LIPUS. It knows only that purring feels in some way that all animal bodies understand below the level of consciousness, right? It knows the way all living things know the things they need, not through reasoning, but through the ancient, wordless intelligence of a body that has been refining its solutions for millions of years. And that, perhaps, is the most calming thought of all, that the body knows, that the sound it makes in its most settled moments, in its most comfortable hours, in the warmth and stillness that it seeks when the world permits, that sound is not arbitrary. It is functional. It is purposeful in the deepest biological sense of that word. It is the sound of a body taking care of itself. Let that land softly. Let it become part of the quiet around you. What purring does to your nervous system. We have spent considerable time in the cat's body. Now let us come home to your body, to what happens physiologically and neurologically when you sit with a purring cat, or even when you listen to the recorded sound of one. The story begins with a nerve. Not a small nerve, not one of the many minor nerves that handle specific local tasks in the body, but the vagus nerve, which is the longest, most widespread, and in many respects most important nerve in the autonomic nervous system. The word vagus comes from the Latin for wandering, and the name is apt. The vagus nerve originates in the brainstem, meanders down through the neck, passes through the chest cavity where it sends branches to the heart and lungs, continues through the diaphragm, and eventually reaches into the abdomen where it connects to the stomach, the intestines, the liver, the spleen, and the kidneys. It is a vast neural highway that carries information in both directions, from the brain down to the organs, and from the organs up to the brain. The vagus nerve is the primary driver of the parasympathetic nervous system, which is the division of the autonomic nervous system responsible for the body's rest and restore mode. You have heard of the sympathetic nervous system, that is the fight or flight system, the one that floods your body with adrenaline when you feel threatened, that speeds your heart and sharpens your vision and sends blood to your muscles in preparation for action. The parasympathetic is its counterpart. When the parasympathetic system is active, the heart slows, the muscles relax, digestion resumes, inflammation decreases. The body begins the work of repair, recovery, and cellular maintenance that it can only do when it is not in crisis mode. The vagus nerve tone, the baseline level of activity in this nerve, sometimes measured through heart rate variability, which is the small rhythmic variation in the time between heartbeats, is an important marker of overall health. People with high vagal tone recover from stress more quickly, have better regulated immune responses, experience lower rates of inflammatory disease, and tend to show better cardiovascular outcomes. People with low vagal tone show the opposite pattern: slower stress recovery, more chronic inflammation, greater cardiovascular risk. And one of the things that activates the vagus nerve, one of the things that increases vagal tone, is slow, rhythmic stimulation in the frequency ranges associated with relaxation. When you sit with a purring cat, several things happen simultaneously. The gentle physical touch of petting the cat, the slow, repetitive stroke of your hand along its fur, stimulates mechanoreceptors in the skin that send signals up through the dorsal root ganglia and into the central nervous system, signals that the brain interprets as calming and safe. The warmth of the animal's body against yours triggers thermoreceptors. The weight of the cat provides gentle proprioceptive feedback, a signal to the joint and muscle receptors that you are in a stable, supported position. And then there is the purr itself, the low-frequency vibration traveling through the air and through contact, potentially stimulating the vagus nerve through a pathway that involves the thoracic mechanoreceptors, the pressure-sensitive cells in the chest. Some researchers have noted that people who sit with purring cats on their chests often spontaneously begin to slow and deepen their breathing, matching the slow, even rhythm of the purr with their own respiratory cycle. This is significant because slow diaphragmatic breathing is itself one of the most reliably effective vagal stimulation techniques known to physiologists. By breathing slowly and deeply, you are directly activating the baroreceptors in the aorta and carotid arteries, which send signals to the brainstem that increase vagal activity and shift the autonomic balance toward parasympathetic dominance. The purr may, in a very real sense, teach your breathing to slow, and your slower breathing then does the rest. The biochemical consequences of this parasympathetic shift are well documented. When vagal activity increases and the parasympathetic system becomes dominant, The adrenal glands reduce their output of cortisol, the stress hormone whose chronic elevation is associated with impaired immune function, disrupted sleep, cardiovascular damage, memory impairment, and many other adverse health outcomes. Cortisol, when measured in saliva or blood, is commonly used as a biomarker for stress, and studies examining cat-human interaction have found measurable reductions in cortisol levels associated with petting a cat and listening to its purr. Simultaneously, the body increases production of oxytocin, sometimes called the bonding hormone, a neuropeptide that promotes feelings of trust, warmth, and social connection. Oxytocin has receptors throughout the brain and body, and its effects are wide-ranging. It reduces anxiety, it promotes generous and prosocial behavior, it modulates pain perception, and it appears to buffer the harmful effects of cortisol. When you pet a cat and the cat purrs in response, oxytocin levels in your blood increase. This has been measured. It is not poetry. It is endocrinology. The brain also releases serotonin in response to the experience of calm, rhythmic sensory input. Serotonin being the neurotransmitter most closely associated with mood regulation, with the subjective feeling of contentment, and with the general sense that things are more or less okay. The combination of elevated oxytocin, reduced cortisol, and increased serotonin creates a neurochemical environment that is, in very concrete biological terms, one of the most conducive possible to sleep, to healing, and to the quiet restoration of a system that has been running hard. And the purr, the sound and vibration of the purr, is functioning as one of the triggers that helps create this environment. There is an additional pathway worth mentioning, which connects the purr to the endorphin system. Endorphins are the body's endogenous opioids, the natural pain-relieving chemicals that are released during exercise, laughter, and pleasurable physical contact. Research suggests that the physical vibration of a purr, felt against the body, stimulates the release of endorphins in the cat and possibly in nearby humans. This is why people with chronic pain conditions, fibromyalgia, arthritis, degenerative disc disease, sometimes describe noticeable relief when a cat rests on or near the affected area and purrs. The effect is not simply psychological comfort, though that is real and meaningful too. The vibration itself may be triggering an endorphin release that provides genuine, biochemically mediated pain relief. One woman interviewed by ABC News described an experience that researchers in the field found illustrative. She had been living with fibromyalgia, arthritis, and degenerative disc disease for more than 20 years. One day she was on her sofa in significant pain, unable to get up, crying from the intensity of it. Her cat, not ordinarily a lap cat, not the kind of animal that typically sought close physical contact, came to her. It climbed onto the sofa, lay down next to her, placed its head on her shoulder, and began to purr. The pain did not disappear, but it eased. She described the sensation as something she could not fully explain. A softening, a bearability that had not been there a moment before. This is not a controlled study. It is a single anecdote, but it illustrates in human terms what the research is reaching for. The idea that the vibration of the purr, delivered at close range to a painful body, may be doing something that we do not yet fully understand, but that is real enough to be felt. Consider what is happening in the body when all of these systems are activated simultaneously. Vagal activity is high, cortisol is falling, oxytocin is rising, serotonin is present, endorphins are released, Heart rate is declining, blood pressure is dropping, breathing has slowed and deepened, and the musculature of the face, jaw, shoulders, and chest has begun to release the chronic tension that most of us carry through our days without noticing it. This is not a coincidence. This is the physiology of safety, of rest, of the state that the body is designed to inhabit when it is not in danger and when it has what it needs. And a small animal lying in your lap or on your chest, generating a sound at 25 to 150 hertz, is apparently one of the most reliable triggers for this entire cascade. There is also a dimension to this that is worth acknowledging directly. The relationship itself matters. The fact that the being generating the purr is alive, warm, breathing, and in some sense choosing to be close to you, that it has, in its particular way, selected your company from all the places it could be, activates social bonding systems in the human brain that are distinct from what you would experience hearing a recorded purr through headphones. The oxytocin response is greater with physical presence. The sense of security that comes from shared proximity with a living creature activates threat detection systems in the brainstem in ways that tell the body, you are not alone, the environment is safe, the other mammal has assessed the situation and found it unthreatening. This is a very old signal. Mammals have lived in social groups for most of their evolutionary history, and the presence of calm, settled companions has always been one of the most reliable indicators that the environment is safe. The purring cat, relaxed and still and vibrating against you, is sending a signal that every part of your nervous system, from the ancient brainstem to the modern neocortex, is equipped to receive and interpret. We did not design this. It is not a technology. It is an ancient biological conversation between two kinds of mammal, conducted in a frequency range below the register of conscious thought, producing effects that run through every organ system in both bodies simultaneously. Your heart, your sleep, and the cat on your chest. We arrive now at the human health data. The specific, measurable outcomes that have been associated with cat ownership, cat interaction, and the particular acoustic and vibrational experience of living with a purring cat. This data has been gathered over decades in multiple countries by researchers studying cardiovascular health, mental health, stress physiology, and sleep quality. It is not perfect data. It is subject to the usual limitations of human epidemiology, including confounding variables and correlation-causation challenges, but the patterns are consistent enough and the proposed mechanisms specific enough to be taken seriously. Let us start with the heart, because the cardiovascular research is the most striking in terms of sheer magnitude. In 2008, Dr. Adnan Qureshi and his colleagues at the Minnesota Stroke Institute at the University of Minnesota published findings from a large analysis of data collected as part of the second National Health and Nutrition Examination Study. The dataset included 4,435 participants who had been followed for 20 years, and it included information about pet ownership, specifically whether they had owned cats at any point during their lives. After adjusting for age, sex, ethnicity, systolic blood pressure, smoking status, diabetes, cholesterol levels, and body mass index, the standard confounders in cardiovascular research, they found that current or past cat owners had a significantly lower risk of death from myocardial infarction compared to people who had never owned a cat. How significant? A relative risk of 0.63, which means that cat owners, even after all those adjustments, were 37% less likely to die from a heart attack than non-cat owners over the 20-year study period. There was also a trend toward reduced risk of death from all cardiovascular diseases combined, including stroke, in the cat owner group, with a relative risk of approximately 0.74. To appreciate how large these numbers are, many pharmaceutical interventions for cardiovascular risk reduction achieve risk reductions in the range of 20 to 30%. The cat data from a population-level epidemiological study shows effects in a similar range. The researchers were careful to note that this does not prove that owning a cat causes better cardiovascular health. Epidemiological correlations are not the same as established causal relationships. But the size and consistency of the association are striking enough that the study attracted considerable attention in the cardiovascular medicine community. A 2013 scientific statement from the American Heart Association reviewed the available evidence on pet ownership and cardiovascular risk, concluding that pet ownership, particularly dog ownership, partly because the exercise associated with dog ownership is a well-understood cardiovascular benefit, is probably associated with decreased cardiovascular disease risk. For cat ownership specifically, the statement acknowledged the Qureshi data and the biological mechanisms that might explain it. Stress reduction, lower resting heart rate and blood pressure, and improved autonomic tone. Multiple smaller studies have added detail to this picture. A study of 240 married couples found that people who owned cats or dogs had significantly lower resting blood pressure and lower blood pressure reactivity to stress than people without pets. A study of 120 married couples that measured physiological responses to stressful tasks found that cat owners had lower resting heart rates and blood pressure before the tasks began, made fewer errors during the tasks, and showed less cardiovascular reactivity to the stress. A 2003 study of 102 patients recovering from heart attacks found that those who owned pets, cats or dogs, had significantly higher heart rate variability than those who did not, and heart rate variability, as we noted in the previous section, is associated with reduced cardiac mortality in this population. The proposed explanation for all of these effects runs through the nervous system pathways we explored earlier. Chronic reduction in cortisol, chronic elevation of parasympathetic tone, chronic improvement in autonomic balance, all of which add up over years and decades to a cardiovascular system that is less stressed, more resilient, and more capable of recovering from the ordinary insults that life delivers. And the purr specifically may be part of this. Not the only part, the companionship, the touch, the emotional support, the social connection provided by a cat all contribute. But the purr adds something specific that those other factors do not. A continuous, low-frequency vibrational and acoustic stimulus that targets the autonomic nervous system and the endocrine system through pathways that are at least partially independent of the emotional dimensions of the human-cat relationship. You can hear a recorded purr without any cat present and still experience measurable reductions in heart rate. You can listen to purring sounds through headphones without any physical contact and still feel your breathing slow. The auditory stimulus alone has physiological effects. This is the basis for the growing field of vibroacoustic therapy as applied to human relaxation and health. A field that is increasingly using cat purr recordings or artificially generated sounds in the 25 to 150 Hz range as therapeutic tools for anxiety, chronic pain, sleep disorders, and cardiovascular risk reduction. Now let us talk about sleep, because this is, after all, a sleep channel, and the relationship between the cat's purr and human sleep is both scientifically interesting and personally relevant to the experience you are having right now. Research consistently shows that cat owners report better subjective sleep quality than non-cat owners. A survey published in 2020 found that a majority of cat owners who allowed their cats to sleep in the bedroom reported that their cats were positive factors in their sleep experience, citing the sense of warmth, comfort, and security provided by the animal's presence. Many specifically mentioned the purring as a sleep aid, a sound that helped them fall asleep and that they found soothing during nighttime awakenings. The mechanism through which the purr supports sleep involves several of the pathways we have already described. The reduction in cortisol makes it easier for the brain to transition from waking to sleep. High cortisol is one of the most common physiological barriers to sleep onset, responsible for the racing thoughts, wide awake at 2 in the morning experience that many people with stress and anxiety know well. The activation of serotonin supports the production of melatonin, which is synthesized from serotonin in the pineal gland and is the primary hormonal signal that initiates and maintains sleep. And the vagal activation that the purr promotes pushes the nervous system toward the parasympathetic state that is necessary for sleep onset, the state in which heart rate falls, digestion resumes, the body temperature regulation appropriate to sleep begins. There is also a simpler mechanism at work. The purr functions as a form of rhythmic, low-frequency sound that masks environmental noise and provides the auditory system with a steady, non-threatening signal to track. This is the same principle as white noise machines, which are widely used as sleep aids and which have reasonable, if not overwhelming, evidence for their effectiveness. The cat's purr, operating in a lower frequency range than typical white noise and with a natural, biological rhythm rather than a mechanically generated one, may be particularly effective at this masking and grounding function. One study found that participants who listened to cat purring sounds for 5 minutes before bed fell asleep faster and reported more restful sleep than a control group. The frequency range of the purr, landing in the region that the auditory system registers as deep, warm, and safe, appears to be particularly good at settling the hyperactive cognitive activity that interferes with sleep onset in people under stress. For people who do not have cats, this is part of the reason that recordings of cat purring have become a significant genre on YouTube and on sleep audio platforms. A search for cat purring for sleep will return thousands of videos with millions of combined views, and the comment sections of these videos are full of people describing the same experience. The sound that starts as something they are paying attention to, and then becomes something they cannot remember falling asleep to, which is exactly the right outcome. The best sleep aids are the ones you forget taking, and that is what the purr offers in the end. Not magic, not medicine in the pharmaceutical sense, but a sound that speaks to something very old in the mammalian nervous system, a sound that says warmth and safety and close and still, in a frequency range that bypasses conscious thought and lands directly in the body. A sound that your cortex never needed to understand, because your brainstem understood it long before cortexes existed. If you have a cat nearby tonight, let it purr. Let the vibration come through whatever surface you both share. Let it do what it has always done, in the way that bodies shaped by millions of years of evolution have learned to respond to it. And if you do not have a cat nearby, you are already listening. And that, it turns out, may be enough. Inspired by the purr. How cats are changing medicine. Before we turn to the solicitation purr and the remarkable acoustic strategy cats deploy with sleeping humans, there is one more dimension of the healing research worth exploring in some depth. The ways in which the cat's purr has not only been studied as a natural phenomenon, but has begun to actively inspire medical technology. The connection between the cat's purr frequency range and bone healing is not merely a theoretical curiosity for academic biologists. It has attracted the attention of engineers, physical therapists, and medical device researchers who are interested in translating the insight into clinical applications. Some of this work is still experimental. Some of it has already entered clinical practice in various forms. Low-intensity pulsed ultrasound, known by the abbreviation LIPUS, is one of the most established examples. LIPUS devices deliver mechanical vibrations to injured tissue at frequencies and intensities that are, in the words of some researchers, remarkably similar to those produced by a cat's purr. The devices are used clinically to accelerate healing of non-union fractures that have failed to heal on their own, and to improve the rate of healing in fresh fractures. The mechanism involves the stimulation of osteoblast activity and the promotion of the cellular signaling cascades associated with bone remodeling, effects that are consistent with the laboratory research on low-frequency vibration and bone tissue that we discussed earlier. LIPUS has been approved by the U.S. Food and Drug Administration for the treatment of non-healing fractures, and evidence for its efficacy is substantial enough that it has been incorporated into orthopedic practice in many countries. Researchers working on LIPUS and related technologies have noted, not without some satisfaction, that cats appear to have been using something like this approach for millions of years. More directly inspired by the cat's purr itself are a category of devices sometimes called vibroacoustic therapy units. Devices designed to deliver low-frequency sound vibrations to the body, either through contact surfaces such as specially designed chairs or tables, or through direct application to specific body regions. The frequency ranges used in these devices overlap significantly with the cat's purring range, and the claimed applications include pain management, anxiety and stress reduction, fibromyalgia symptom relief, and improvement in joint mobility. The evidence base for vibroacoustic therapy is growing, though it remains less robust than for LIPUS specifically. There is also research being done on the use of recorded cat purr sounds, not as a relaxation tool, but as a specific therapeutic stimulus. Some researchers have investigated whether playing cat purr recordings to patients with anxiety disorders produces measurable physiological effects comparable to those seen with other forms of sound therapy. Early results, while not yet definitive, are consistent with what the mechanism would predict. Reductions in heart rate, reductions in salivary cortisol, self-reported decreases in anxiety, and improvements in subjective sense of well-being. The most poetic application, in both senses of the word, since it is both imaginatively appealing and still somewhat speculative, is the idea of using cat purr frequency vibration in the treatment of astronauts on long-duration space missions. The bone density loss associated with extended exposure to microgravity is one of the serious medical challenges of deep space exploration. Current countermeasures include vigorous exercise protocols, but exercise in microgravity is complicated by both the physical constraints of the environment and the time it consumes in an already demanding schedule. Low-frequency vibration therapy at cat purr frequencies, delivered passively through contact surfaces in sleeping quarters or work areas, has been proposed as a complementary approach that could provide bone maintenance stimulus without requiring additional time or effort from the crew. Elizabeth von Muggenthaler, the researcher whose systematic recording and analysis of purring felids established the frequency data most often cited in this field, explicitly noted the NASA connection in her original research. She pointed out that cats have adapted to conserve energy through long periods of rest, and that purring at bone-stimulating frequencies may be an elegant solution to the problem of maintaining musculoskeletal health in an animal that spends most of its time physically still. The parallel to astronauts in microgravity is not superficial. Both populations face the challenge of maintaining bone health without the normal weight-bearing activity that drives bone remodeling on Earth. Whether or not this specific application ever becomes part of standard space mission protocol, the conceptual contribution is significant. The idea that a biological system, operating in an animal that humans have lived with for 10,000 years, had quietly solved a problem that aerospace medicine researchers were struggling with, and had done so using nothing more sophisticated than the vibrating throat of a resting animal. There is a broader lesson in this, one that biologists and engineers and physicians have been articulating with increasing urgency over the past several decades. Nature has been running experiments in engineering, chemistry, and medicine for 4 billion years, and the solutions it has arrived at often outperform what human ingenuity can devise from scratch. The field of biomimicry, the deliberate study of natural systems for the purpose of applying their solutions to human engineering challenges, is built on this recognition. Velcro was inspired by the way burdock seeds stick to animal fur. Water collection systems have been inspired by the Namib desert beetle, which harvests fog from the air using a surface textured with alternating hydrophilic and hydrophobic spots. Increasingly efficient solar cells have drawn on the structure of moth eyes, which are textured in ways that minimize light reflection. The cat's purr belongs in this tradition. It is a technology. It is an ancient, elegant, low-energy, continuously available technology for delivering specific mechanical frequencies to biological tissue for the purpose of maintaining that tissue's health. The cat did not design it. Evolution designed it through the slow, patient, iterative process of selecting for outcomes that worked, and it has been running reliably without maintenance or upgrades for somewhere between 6 and 25 million years. The next time you hear a cat purring, you might think of it that way, not just as a sound, not just as an expression of contentment, but as a piece of biological engineering whose specifications happen to match with remarkable precision the specifications that modern medical research has independently identified for therapeutic vibration therapy. The body is smarter than we are. It has always been smarter than we are. We are just beginning very slowly to understand what it already knows. The solicitous purr when cats ask, and why we listen. There is one more layer to the cat's purr that we have not yet fully explored, and it is perhaps the most interesting from the perspective of the human-cat relationship specifically. It concerns a variation on the standard purr, a modification so subtle that most cat owners have heard it thousands of times without consciously identifying it as different, but one that researchers have shown has a measurable effect on human behavior. In 2009, Dr. Karen McComb and colleagues at the University of Sussex recorded cats in two situations. In ordinary relaxed contexts, purring contentedly without any goal related to food or attention, and in situations where the cats were attempting to wake their sleeping owners for an early morning feeding. The researchers analyzed these recordings acoustically and found something fascinating. The purrs produced in the hunger context were not simply louder or more insistent versions of the ordinary purr. They had a different structure. Embedded within the low, rolling rhythm of the standard purr was a higher frequency component, a cry-like element with acoustic properties similar to the vocalization patterns of distressed human infants. This embedded cry sat within a frequency range, roughly 300 to 600 Hz, that human auditory systems are specifically tuned to detect and respond to. The sound of a distressed infant is, for most adult mammals and particularly for adult humans, one of the hardest sounds to ignore. Evolution has shaped us to be alert to it, to feel urgency in response to it, to want to do something about it. And the cat apparently has learned, across its centuries of domestication and its close observation of human behavior, to put that frequency inside its purr when it wants something. McComb's team played both types of purr recording to human listeners and found that the listeners consistently rated the embedded cry purr as more urgent and more unpleasant, even when they did not consciously identify the two versions as different. They felt something in one that they did not feel in the other, a kind of low-grade pressure, a sense that something needed attention. And critically, this effect was present even in people who did not own cats. The researchers played the recordings to people with no cat experience, and those listeners also found the solicitation purr more urgent. The response was not learned through familiarity with cats. It was accessing something more general, the human sensitivity to distress frequencies in the auditory range that infants use. This is one of the more remarkable examples of what biologists call cross-species acoustic exploitation. An animal learning to embed signals that target the sensory biases of another species in order to elicit a desired response. The cat did not design this consciously. The cats that happened to embed this frequency in their hunger purrs were cats that got fed sooner and more reliably, and over generations that behavior became more common. Natural selection, running on the simple fuel of food access, produced a sound that can reach into a sleeping human's dreaming brain and make them feel that something needs attending to. It is worth noticing, as we sit with this, that the cat's relationship to the purr is not one thing. It is not simply contentment, and it is not simply self-soothing, and it is not simply a healing mechanism, and it is not simply a mother-infant signal, and it is not simply a manipulation of human feeding behavior. It is all of these things, simultaneously, serving different functions in different contexts, generated by the same basic mechanism but modulated in subtle ways that serve entirely different communicative and biological purposes. The purr is, in this sense, a remarkably versatile instrument. More versatile in some ways than the meow, which is more variable but also more context-specific. The purr runs across nearly every dimension of feline life: birth, infancy, bonding, self-care, pain management, social signaling, and the particular kind of cross-species communication that has come to define the domestic cat's relationship to the humans it lives with. It is at once the oldest sound in the cat's vocal repertoire and one of the most behaviorally flexible. This versatility itself is worth a moment of appreciation. Most biological structures evolve for a specific function and remain tied to that function. The eye evolved to detect light, and it detects light. The ear evolved to detect vibration in air, and it detects vibration in air. But the purr appears to have been recruited, across the history of feline evolution and domestication, into an ever-expanding range of uses, growing from a simple mother-infant communication signal into a complex, multifunction acoustic and vibrational tool that serves the cat's health, its emotional regulation, its social relationships, and its relationship with an entirely different species. If you want to understand what evolution can do given enough time and enough selective pressure, you could do worse than to study the purr. Sound, rhythm, and the sleeping brain. Let us return now to sleep, specifically to what happens in the brain during the transition from wakefulness to sleep, and why the particular properties of the cat's purr are so well matched to that transition. Sleep onset, in the language of neuroscience, involves a progressive slowing of brain wave activity. When you are fully awake and alert, your brain is dominated by high-frequency electrical activity, beta waves, in the range of 13 to 30 Hz. As you begin to relax and move toward drowsiness, this shifts to alpha waves in the range of 8 to 13 Hz, waves associated with relaxed wakefulness, with the state of mind that meditation practitioners and teachers sometimes describe as alert stillness. As you move deeper into drowsiness toward the first stage of sleep, the activity slows further to theta waves in the range of 4 to 8 Hz. Waves associated with the hypnagogic state, that threshold experience of half-dreaming, of images that appear and dissolve, of thoughts that lose their narrative logic and become briefly, beautifully strange. And then, when true sleep arrives, the brain drops into delta waves, the slowest of all below 4 Hz, the signature of deep, restorative, slow wave sleep. The transition from alert to asleep is, in this neurological sense, a journey through progressively slower frequencies. And one of the things that facilitates this journey is the presence of a rhythmic, low-frequency external stimulus that the brain can use as a pacing signal. This is the mechanism behind white noise machines, behind rain sounds, behind the drumming rhythms used in certain meditation and trance traditions across cultures. The external rhythm provides the auditory cortex and the associated brain networks with something slow and repetitive to engage with, which gradually pulls the brain's own rhythms in the direction of that slower pace, a phenomenon called auditory entrainment or brainwave entrainment. The cat's purr, sitting at 25 to 150 Hz, is not itself in the frequency range of brain waves, but its rhythmic structure, the steady metronomic quality of the purr, provides a consistent temporal framework that the brain can track, and the low-frequency, non-threatening character of the sound is consistent with the auditory environments most strongly associated with safety and rest in our evolutionary history. The effect is a gentle downward pull on arousal, a cue to the sleeping circuitry that it is acceptable to let the vigilance systems relax. There is also a role for the physical vibration here, distinct from the auditory component. The body surface, when in contact with a purring cat, receives mechanical vibrations that the somatosensory system processes as a kind of rhythmic touch. Slow, rhythmic touch, the kind that parents instinctively use with infants, is one of the most reliable activators of the parasympathetic nervous system and one of the most effective ways to promote sleep in aroused individuals. The purr delivers this rhythmic touch continuously, without interruption, through the simple physics of vibration conducted through contact surfaces. In this way, the purr is functioning simultaneously as an auditory sleep aid, a tactile sleep aid, and a neurochemical sleep aid through the cortisol reduction, the oxytocin elevation, and the serotonin to melatonin pathway we described earlier. It is hitting multiple sleep-promoting systems at the same time through different physical and physiological channels. This is why the experience of falling asleep to a purring cat is so often described as different from other sleep experiences. More complete, more settled, more like falling into warmth rather than just falling into darkness. The brain is not just shutting down. It is being gently, thoroughly, systematically prepared for rest by a sound that speaks to every relevant pathway simultaneously. And for those who listen to recorded purrs without the physical presence of the cat, much of this still applies. The auditory component, the cortisol effects, the brainwave entrainment, the sense of rhythmic steadiness travels through headphones or speakers with full fidelity. What is lost is only the direct physical vibration of the contact, and for many people that is not the limiting factor in their sleep difficulties. The sound alone, for many, is sufficient. This is why you are here, and this is why this works. The philosophy of the purr, what it teaches us about rest. Before we reach the closing, I want to spend a few quiet minutes with something that is less biology and more reflection. Not a departure from science, but an extension of it into the territory where science and meaning meet. One of the things that is most striking about the cat's purr, when you understand its mechanism and its function, is what it says about the relationship between rest and repair. We live in a culture that tends to regard rest as passive, as absence. The absence of activity, the absence of productivity, the absence of useful engagement with the world. Rest, in this framing, is what you do when you have finished doing. It is the gap between efforts. It is permitted, but it is not itself worthwhile. It is recovery, not action. The cat's purr challenges this framing in a specific and vivid way. The cat, lying still for 16 hours, is not simply pausing between activities. It is doing something. Something measurable, something physiologically productive, something that maintains the integrity of its bones and its muscles and its joints in ways that allow it to perform extraordinary athletic feats when the moment for athleticism arrives. The stillness is not absence. The stillness is medicine. The sound that fills the stillness is not merely comfort. It is biological work, accomplished at the cellular level through the medium of vibration. The body knows how to use rest. The body has, over the course of millions of years, developed sophisticated systems specifically for the purpose of using rest productively, systems of repair and maintenance and rebuilding that can only run when the organism is not engaged in demanding external tasks. Sleep, with its slow-wave stages of physical restoration, is the most obvious of these systems. But the cat's purring adds another dimension to this picture. The idea that even the sounds a body makes in its most rested state are not random or purposeless, but are part of an integrated biological response to the condition of being still. When we lie down at night, something similar is happening in us, though without the purr. The heart rate slows. Growth hormone is released, which drives tissue repair and cellular renewal. The immune system becomes more active, patrolling and repairing with a thoroughness that the metabolic demands of wakefulness would not permit. The brain consolidates memories and processes emotional experiences in ways that improve the psychological resilience and clarity available to the waking mind. The sleeping body is not quiet in the sense of doing nothing. It is profoundly, elaborately busy, doing work that cannot be done any other way. The cat's purr, in this context, is a reminder that rest is not simply the absence of effort. It is its own kind of effort, an active process, running on ancient biological machinery, producing outcomes that matter. And the sound of the purr is the audible signature of that process. The sound of a body that has learned, across millions of years, to do something useful with the gift of stillness. There is a kind of permission in that. A reminder that lying here, in the quiet, allowing the minutes to slow and the breath to deepen, you are not wasting time. You are not failing to do something you should be doing. You are participating in one of the most ancient and most necessary biological processes that evolution has developed. The cat purrs in its sleep. You breathe in yours. The frequency is different, but the principle is the same. The body, given permission to rest, knows exactly what to do. The deepest frequency. We have traveled a long way tonight, from the first awareness of that low, steady hum, through the architecture of the larynx and the physics of vibration, through millions of years of evolution and the intimate early world of kittens pressed against a warm body in the dark. We have sat with the numbers, 25 hertz, 50 hertz, 150 Hz, and understood what they mean not just as acoustic measurements but as biological facts with consequences for bone and blood and the slow, steady pulse of the heart. We have followed the signal through the nervous system, watched it arrive at the vagus nerve and cascade through endocrine system and brainstem and the whole biochemistry of rest. We have heard about the solicitation purr embedded with the frequency of an infant's cry, and we have marveled at what evolution can accomplish when given 10,000 years and a willing species on each end of the arrangement. And perhaps most importantly, we have recognized in all of this something that does not require a laboratory to feel but is made richer by understanding. That the connection between a human being and a purring cat is not merely sentimental, not merely cultural, not merely the accumulated habit of 10,000 years of domestic life together. It is a biological fact. It is a measurable, repeatable, mechanistically explainable fact. The sound does something to the body. The body responds in ways that are measurable and specific and, by the evidence available to us, generally beneficial. There is a comfort in that, even beyond the comfort of the purr itself. We live in a time when so much of what we are told is good for us requires effort and technology and intervention and expertise. But here is a thing, this ancient, warm, low-frequency thing, that asks nothing except proximity and stillness. The cat does not need you to do anything. It needs only that you are there, that you are quiet, that you allow the contact. And in return, without transaction, without negotiation, it generates a sound that your nervous system was shaped over millions of years to find calming. The cat is old. The purr is older. And the part of you that responds to it, the part that feels your shoulders drop and your jaw unclench when you hear it, the part that doesn't need to be explained to, the part that simply knows, that part is older still. It is worth sitting with that for a moment at the end of this long journey through the science. We have learned a great deal tonight about neural oscillators and vocal fold pads and the myoelastic aerodynamic theory of phonation. We have learned about osteoblasts and RUNX2 and trabecular bone density. We have learned about the vagus nerve and the parasympathetic nervous system and the role of cortisol in cardiovascular disease. We have learned about hyoid bones and the evolutionary divide between purring and roaring, about the genetics of cat domestication and the acoustic fingerprinting of individual feline identity. And at the end of all of it, we arrive back at the same place we started. A warm room, a low light, and a sound so simple that a creature born blind can feel it through the walls of a nest. 25 cycles per second, 50 cycles per second. The low, continuous, unbroken hum that says, I am here, I am safe, and so, by implication, are you. There is a line of research, still preliminary, still exploratory, that suggests human beings can generate something similar through the act of humming. When you hum, the vibration of the vocal folds sends mechanical stimulation through the bones of the skull and the structures of the face and neck. The vagus nerve, connected to the vocal cords, is stimulated by the vibration. The frequency range of a low, comfortable hum sits in roughly the same territory as a cat's purr. Monks who chant, practitioners who use sound bowls, throat singers in the Tuvan and Tibetan traditions, all of them appear to be accessing some version of the same biological pathway, using self-generated vibration to calm the nervous system, reduce physiological stress markers, and create the internal conditions for rest and clarity. The cat does not know it is doing something that humans have independently rediscovered and formalized into meditation practices. It simply vibrates. It simply rests. It simply generates, as naturally as breathing, the frequency that its body has always known it needs. Tonight, you are receiving that frequency. Through the audio, through whatever device is carrying this voice to you, through the specific and scientifically documented effects of rhythmic low-frequency sound on the human nervous system at rest. You are participating, whether or not you knew it, in something ancient and biological and surprisingly well-researched. So tonight, wherever you are, whatever the day has been, you are here. The sound is here. The night is quiet around you, and inside the quiet, if you listen, there is that low and steady hum, in a recording, in a memory, in the warm weight of an animal curled at the foot of your bed. 25 cycles per second, 50 cycles per second. The rhythm of a body taking care of itself, and in the taking care, somehow taking care of you too. Let your eyes go soft. Let the breath slow. Let the frequency find you. Has always known where you are. If this journey has been useful to you, if you fell asleep before the end, which is the highest compliment you can give a sleep channel, please consider leaving a like and subscribing to Deep Science Sleep. We explore the science of the sleeping world, one calm and carefully researched night at a time. And if there is a topic you would like to fall asleep to, a piece of biology, a corner of neuroscience, a question you have wondered about in the quiet hours, leave it in the comments. We read everything. Asterisk. Sleep well. Science is watching over you. Asterisk.